Good day, everyone. I am Dr. Solomon Moneri of the Department of Biomedical Engineering, University of Lagos, Nigeria. I'll be taking you this course, BME 312 Transducers. Here are some of our recommended texts for the course. The course outline for this course is listed on the slides. Lesson 1 is Introduction to Transducers and Definition. Lesson 2 will talk about transducer types, electrical, electromechanical, and electrochemical transducers. In Lesson 3, we will continue our discussion on transducer types, and we'll look at temperature, pressure, and pneumatic transducers. In Lesson 4, we will also continue our discussion on transducer types. Our focus will be inductive and capacitive transducers and biological transducers. In Lesson 5, we'll discuss chemical and photoelectric transducers, their characteristics, operations, and applications. In Lesson 6, we will discuss output device transducers, meters, strip chart recorders, oscilloscope. In Lesson 7, we'll look at output device transducers, and the specific aspects will be displays, lamp indicators, heaters, and polygraphs. In Lesson 8, we'll discuss input devices. In Lesson 9, we'll look at magnetic transducers, strain gauge transducers, linear variable differential transformer. In Lesson 10, we discuss resistance temperature detector. 11, we look at transducer signal sources amplification and transmission. While in Lesson 12, we discuss signal conditioning circuits. So let's start with our lecture for today. As I told you earlier on, this course is BME 312 Transducers. So today we'll look at Lesson 1, Basic Introductions and Definition. The lesson objectives for today's lecture is to define a transducer and explain its basic function, to explain the fundamental concepts in biomedical measurement techniques, explain the difference between signal and noise, and explain the various input-output characteristics of a measurement system. So, what is a transducer? A transducer is a device that converts energy from one form to another. So, when energy enters a device and is converted from one form to another, that is a transducer. So generally in medical devices, transducers convert signals of various physical forms to electronic signals for further processing. That is very important because most of the biological signals that are to be measured by a medical device are usually physical quantities like temperature, pressure, and the rest of them, which need to be converted to electrical signals before they can be processed by the medical device. So that is what a transducer does. It does this conversion. So when you take your, say, blood pressure monitor and try to measure blood pressure from a person, what it detects from the person is a physical quantity, which is the pressure. That pressure for the medical device to be able to pressure, to be able to measure that pressure, it needs to be converted into an electrical signal, which the system will be able to understand. So that is why a transducer is important. The basic functions of a transducer are: the first is to sense the presence, magnitude, or change in or pressure of some measurand. So a transducer senses the presence of a measurand. The measurand in this case are the physical quantity that is to be measured. The physical quantity that you want to measure is referred to as the measurand. So the transducer detects that physical quantity, it senses it. The second function of a transducer is to provide an electrical or mechanical output that furnishes the accurate quantity of data to be measured. So it converts that physical quantity into an electrical signal. The transducer, the second function is to convert that physical quantity it has detected into an electrical signal. That is the second function of a transducer. Let me summarize it again. The first function is to sense the presence of the physical quantity that you want to measure, while the second function is to convert that physical quantity that it has detected into an electrical signal. So the basic parts of a transducer: the first is the sensing element. The sensing element is the part of the transducer that detects or responds to any changes in the physical features. So that is the sensing element. Usually the response is dependent on the physical phenomena that you are trying to measure, whether it's pressure change or motion change. That is what will determine the kind of response from the transducer. The transducer also has the transduction element. The transduction element converts the sensing element response output into a standard electrical signal, usually in voltage or current. So basically that's what the sensing element, the transduction element does. The transduction element converts the sensing element response output to an electrical signal in the form of voltage or current. And this aspect also involves signal processing or conditioning. So let's look at what a sensor is. A sensor is a device that detects and responds to some type of input from the physical environment. That is what a sensor is. The sensor detects the physical quantity to be measured. The input can be heat, pressure, and motion. What are the basic differences between a transducer and a sensor? One, the basic thing you must understand is that a transducer, a sensor is a subset of a transducer. A sensor is a subset of a transducer. So let me summarize it here. The three points that we have listed. One, the sensor converts physical quantity into electrical equivalent quantities, such as resistance, inductance, capacitance. The transducer does not always convert physical quantity into electrical quantity. It can convert an electrical signal into physical quantity as well. That is another important point you must note. A transducer can convert an electrical signal to a physical quantity. but the sensor cannot do that. Then 2, a sensor has no signal processing function. It does not perform signal processing, while a transducer can perform signal processing, such as signal filtering, amplification, and signal attenuation or modulation. Also, a sensor is a part of the transducer system, as I said earlier on. While a transducer has the section that is the sensor, that is the sensing element, as well as the transduction element. Let's also look at some other basic definitions. 1, measurement. What is the meaning of measurement? A measurement is a procedure that makes it possible for an observer to determine the quantity that is to be measured or that characterizes a property. For instance, if I have a blood pressure monitor, how do I know the blood pressure of a particular person if I don't measure it? So, measurement involves being able to detect the quantity of a physical property. Also, in terms of measurements, the measurement of 100 meters is 100 meters. So if there is no measurement, you'll not be able to know the specific value of a quantity. Measurement makes it possible for us to know the specific value of a quantity. Another important definition we must note is signals. In a measurement, the signal is defined as a component of a variable which contains information about the object quantity. The signal is defined as a component of a variable that contains information about the object quantity. Also, let's look at the meaning of noise. Noise is a component unrelated to the object quantity of interest. Noise is a component unrelated to the object quantity of interest. For instance, you have signals that you want to measure in a particular person, and there are other signals that are preventing you from being able to get an accurate measurement. Those other signals are referred to as noise or disturbances, usually called noise disturbances, that prevents you from being able to detect the accurate value of what you want to measure. So a noise is usually a disturbance. For instance, in biopotential measurements, electromyogram, which measures the potential generated by muscles, gives information about the muscle activity. Thus, the electromyogram is considered a signal in this case. But the electromyogram is an unwanted component for another observer who is interested in obtaining nerve potentials. So if another observer wants to measure nerve potentials and electromyogram is affecting the quantity that is to be measured, in that case it has become noise. Now let's look at signal to noise ratio. The signal to noise ratio is a ratio of the value of the signal to that of noise. It is the ratio of the value of signal compared to that of noise. It is referred to as the signal to noise ratio, SNR. The SNR is measured in decibels. SNR is measured in decibels. So the ratio of power of signal to noise is calculated as SNR is equal to 10 log base 10 signal divided by noise. That is the ratio of power of signal to noise. We also have the ratio of amplitude of signal to noise. If it's the ratio of amplitude of signal to noise, is calculated as the signal to noise ratio is calculated as 20 log 10 S over N, that is signal divided by noise. So let's look at transducer and measurement system. A measurement system consists of the transducer and the electric instruments. The physical or chemical quantity that characterizes the object is detected by the transducer. So the transducer detects the physical or chemical quantity that is to be measured. And this quantity is converted into electrical quantity, which is displayed by using an appropriate electronic instrument, which will reveal the results to an observer. You should note that the transducer is an essential part of a measurement system because the quality of the measurement is determined mostly by the transducer that is used. Different types of object quantities require different types of transducers. So depending on the type of quantity that you want to measure, it also determines the type of transducer that is needed. Different types of transducers are also required according to the requirements of different measurement situations, such as different signal amplitudes and frequency ranges. Accuracy requirements, limitations in size, shape, or materials, or invasiveness of the measurement procedure. Here is a block diagram of a measurement system. As you can see in the block diagram, the first block is the object of measurement. The first block is the object of measurement. The particular quantity you want to measure is on this first block. So that quantity, it can be temperature, it can be pressure, it can be light. When it enters a transducer, the transducer transduces the signal. What it means by transducing the signal, first, it detects the signal that is to be measured. Then it converts it to an electrical signal. That electrical signal enters the electronic instrument and it displays the particular output. That is the result of what has been measured. So the observer, the person that is trying to take the measurement, can see the result of what is being measured. Here is another block diagram that shows the elements of a measurement system. We can see the measured variable, which is the measurand that they are trying to measure. For instance, temperature, body temperature, or for instance, blood pressure. The measurand is the quantity that you want to measure. When it enters the sensor detects the quantity that is to be measured and sends the signal to a variable conversion element, which converts it to an electrical quantity. Then sends also signal conditioning and signal filtering is performed. Signal conditioning and filtering help to remove noise and also to amplify the signal. The signal is then processed. Processing involves detecting the value of the signal that has been measured, interpreting the value of the signal that has been measured. Then the output is shown on the display unit, which you see. When you take a measurement, you quickly see the output on the display unit. Usually, all this happens in a matter of seconds. So the layman that does the measurement does not know the processes that have taken place when you do a measurement for the value to be displayed in an output. The first element in any measuring system is the primary sensor, which detects the input from the physical environment. So the first element of any system to be measured is the sensor. So for most, but not all sensors, this function is at least approximately linear. Usually this function is a linear function. Then we also have one or more secondary sensors that are needed if the characteristics of the primary sensor are affected by the environmental condition in which the primary sensor is operating. These measure the environmental conditions and allow the appropriate corrections to be made to the measurements provided by the primary sensor. Then we have conversion elements. Conversion elements are needed when the output variable of a primary transducer is in an inconvenient form, and this output variable has to be converted to a more convenient form. For instance, the displacement measuring strain gauge has an output in the form of a varying resistance. So the resistance change cannot be easily measured. Because we cannot easily measure the resistance change, what is normally done is that we often use a bridge circuit, which is a typical example of a conversion element. The bridge circuit is a typical example of a conversion element. In some cases, the primary sensor and conversion element combined, the combination is known as transducer. Let's look at some characteristics of the measurement system. Characteristics of the measurement system. The first main characteristics we'll look at is static characteristics. Static characteristics. This refers to a situation in which the input-output relationship of a measurement system can be uniquely determined without relying on changes in time. Yes, the input-output relationship is not affected by change in time. This is referred to as static characteristics. The input remains constant or changes slowly. The input remains constant or changes slowly. Some of the static characteristics listed include sensitivity, resolution, reproducibility, measurement rate, linearity, and hysteresis. Let's look at some of them. Sensitivity is an absolute quantity. The smallest absolute amount of change that can be detected by a measurement. Sensitivity is an absolute quantity, that is the smallest absolute amount of change that can be detected by a measurement. When some devices, some measuring instruments, that's small change that can be detected by a measurement is referred to as sensitivity. It's referred to as sensitivity. So sensitivity of a transducer or measurement system is high when a small change in object quantity causes a large change in its output. When a small change in the measurement quantity causes a large change in the output is referred to as sensitivity, a high sensitivity. Then resolution. Resolution is the least value of the object quantity that can be distinguished at the output of the measurement system. That is the resolution. This least value or the smallest value of the quantity that can be distinguished by a measurement system. The smallest quantity that it can measure is resolution. Reproducibility describes how close to one another repeated outputs are when the same quantity is measured repeatedly. That is reproducibility. For instance, I take my blood pressure now and get specific results. If I take it 5 minutes time and get exactly the same results, we say the value is reproducible, although we know that blood pressure changes rapidly. But let's look like, for example, temperature. If you use a thermometer to take my body temperature, and in the next 1 or 2 minutes, you take the body temperature again, and it gives you exactly the same value, we say it is reproducible. Then let's look at measurement range. This is the total range of the object quantity within which the measurement system works so as to meet the nominal performance of the measurement system. Then linearity or non-linearity. Linearity describes how close the input-output relationship of the measurement system is to an appropriate straight line. When you plot a graph and you get the values as a straight line, we say it is linear. But if the values do not give you a straight line, then it is non-linear. So as a quantitative measure of the linearity, the maximum deviation of the input-output relation curve from the straight line is used. However, non-linearity is conventionally used to indicate this value. Then the next is hysteresis. Hysteresis is a kind of phenomenon in which different output values correspond to the same input, no matter how slow the speed of change of the system is. Yes, what happens in hysteresis is that when you supply the same input value to a measurement and it's giving you different output values, we say that there is hysteresis. Now let's look at dynamic characteristics. The dynamic characteristics of a measurement system refers to its behavior when subjected to inputs that are not static but dynamic. So we refer to dynamic characteristics of a measurement system to be its behavior when subjected to inputs that are not static, inputs that are constantly changing. This means that the input of measured variable varies rapidly with time. The inputs you are trying to measure keeps changing rapidly. We say they are dynamic characteristics. It can be described as a transient input-output relation. The time-varying pattern of the object quantity is observed as a waveform. Dynamic characteristics are particularly important when the transducer is part of a control system. The types of inputs that can be measured in terms of the dynamic characteristics of a measurement system, there are basically three. The first is step input. Step input involves step input changes instantaneously by a finite value and then remains constant. It changes and remains constant. The second is linear input. The linear input varies linearly with time, while we have the sinusoidal input that changes sinusoidally. The dynamic characteristics of measurement system. How do the following dynamic characteristics affect a measurement system? You should try and find out how these characteristics affect the dynamics of a measurement system: fidelity, speed of response and response time, lag and dynamic error. So now let's look at first and second order system. The first order system is when the input-output relation of a system is described by a constant coefficient, first order differential equation. The system is called a first order system. A first order system is one in which the input-output relation of the system is described by a constant coefficient, first order differential equation, as shown in equation 1.3. A1 dy dt of t plus A0 y of t is equal to x of t. This is typically an example of a first order differential equation, where x of t and y of t are the inputs and outputs of the system, and A0 and A1 are the constants. So that's a typical example of a first order differential equation. So a measurement system that works based on the first order differential equation can be based on this equation. The frequency response of a first order equation is shown in figure 1.2, which is this graph. So this is a frequency response of a first order system. Then we have the second order system. The second order system is a system that can be described by a second order constant coefficient differential equation, written as A2 the 2y of t over the t squared plus A1 the y of t over the t plus A0 y of t is equal to x of t, as shown in equation 1.4. The frequency response of the second order system is represented in the next graph, which is this graph. The frequency response of a second order differential equation is shown in this graph. So thank you for listening. Thank you very much.